Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Physics. Kungliga Vetenskapsakademin har idag beslutat att utdela 2025 års Nobelpris i fysik till John Clarke, University of California, Berkeley, USA, Michel Devoret, Yale University och University of California, Santa Barbara, USA, och John Martinis, University of California, Santa Barbara, USA, för upptäckten av makroskopisk kvantmekanisk tunnling och energikvantisering i en elektrisk krets. The Royal Swedish Academy of Sciences has today decided to award the 2025 Nobel Prize in Physics to John Clarke, University of California at Berkeley, USA, Michel Devoret, Yale University and University of California at Santa Barbara, USA, and John Martinis, University of California at Santa Barbara, USA, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit.
Two neutrons and two protons is part and bound to the nucleus by a barrier. And classically, it would never ever leave the nucleus. However, due to quantum mechanical tunneling, it can appear outside of the nucleus, and thus you have radioactive decay. And the fact that it's quantum mechanical tells that it's a completely random process. And also by calculating the width and the height of the barrier, you can calculate the average waiting time for this decay or the half-life. This was a question raised by Nobel laureate Anthony Leggett in 1978. He suggested that it should be possible to observe something called macroscopic quantum tunneling in a superconducting circuit. So how should we understand this? Well, in the upper picture here, you see a normal conductor. In the normal conductor, the electrons are very individual. They are fermions, and they are very easily distracted. So if you push a current through this conductor, the electrons are easily distracted, and there is resistance. Thus, you always get the voltage across this conductor. In the second picture, you see how a superconductor works. Here, the electrons take each other two and two by the hand, and then it's much harder to distract them. So then they can lead the current without any resistance at all, so there is current without any voltage together, and they all condense into one macroscopic state. So it's one Cooper pair condensate, which is determined by one macroscopic wave function or a superconducting order parameter. And you see there is a small gap between the two conductors in the lower picture, and that's a so-called Josephson junction. Our three laureates they push a current through the junction, and it was in a state so that it should not classically be able to switch. And yet it switches from the zero voltage state to the state with the voltage. Although classically you see that it cannot switch. John Martinis was a senior PhD student at the time, and Michel Devoret was a postdoc coming from Saclay outside of Paris, with experience from low temperature physics, a little bit less abstract. I also want to show you a modern quantum chip. So the silicon chip is the square in the middle here. They have taken quantum tunneling and quantum physics from the subatomic world onto electric chip. So now we have 40 years of lots of groups in the world exploring quantum physics on a chip, engineering artificial atoms, exploring quantum physics in regimes which are hard to get to with natural atoms, because you can engineer these artificial atoms. you can also couple the superconducting atoms to mechanical oscillators, and then you probe quantum properties of mechanical oscillators.